You know, if you're wrestling with how the tiny microscopic world of quantum mechanics somehow connects to the big measurable world of chemistry, things like why a gas expands or how fast a reaction goes well, you're really hitting the core question of physical chemistry. It can almost feel like two separate subjects sometimes.
It really can.
But today, we're diving deep into the concept that really bridges those two worlds, statistical thermodynamics.
That's exactly right. And our goal here, our mission in this deep dive, is basically to give you a shortcut to understanding that link. Statistical thermodynamics provides the mathematical tool to figure out all those bulk properties, energy, entropy, equilibrium, constants.
The things you actually measure in the lab.
Exactly. And we calculate them using just the molecular details, the kind of stuff you get from spectroscopy, like energy levels. We're essentially taking quantum data and translating it into classical thermodynamics.
So connecting the dots between, say, the energy levels of one molecule and the properties of a whole mole of gas in a flask. And the cornerstone, the absolute foundation for this whole thing, is probably the most important idea in chemistry.
Yeah.
The Boltzmann distribution. Okay, let's get into that.
Right, the Boltzmann distribution.
Yeah.
It's really the master equation. It tells us exactly how molecules are spread out among all the possible energy states when a system's just sitting there at thermal equilibrium. It answers, where are the molecules, energy-wise, at a certain temperature?
Okay, so to figure that out, we have to imagine taking a snapshot, right? What the book calls an instantaneous configuration. And this snapshot tells us, okay, this many molecules are in the ground state, energy epsilon 0, this many are in the next state, epsilon 1, and so on. We write it like N.
Exactly. And then the question becomes, if we have different ways to arrange those molecules, different configurations, which one is, most likely, that's where the idea of weight, capital W, comes in.
Right.
The weight is just the number of distinct ways you can achieve that specific arrangement, NEAAA, by just shuffling the individual molecules. If you've got n total molecules, you calculate W by taking n factorial and dividing by the factorials of the populations in each state, nf factorial, nf factorial, and so on.
And the amazing thing, statistically, is that for any system with loads of molecules, macroscopic systems, it's overwhelmingly likely to be found in the configuration that has the biggest weight, the maximum W.
Right, W max. But finding that configuration isn't totally free. We have two really important rules, constraints. The total energy, E, has to stay constant.
Okay.
And the total number of molecules, N, also has to stay constant. You can't just add or remove energy or particles.
So how do we find the maximum W while sticking to those rules? That sounds like a tricky math problem.
It is a bit involved. It requires a technique called Lagrange's method of undetermined multipliers. It's a standard tool for constrained optimization.
Okay, yeah, I remember that. But let's skip the gritty math details. What's the big takeaway? The physical insight.
This is where it gets really cool. After you work through that derivation, you find something remarkable. The most probable populations, how many molecules are in each state, depend on just one single parameter.
Just one.
Just one. Mathematically, it comes out as beta, sternotes. And then, through some more steps, we prove rigorously that this Joe has to be equal to 1 divided by kT, where K is Boltzmann's constant and T is the absolute temperature.
Wow.
This is huge. The math itself forces us to conclude that temperature is the unique parameter that dictates how molecules spread out among energy states. It's like the molecular justification for temperature even existing.
So temperature isn't just something we measure with a thermometer. It fundamentally governs the distribution at the molecular level.
Precisely. And in practice, the distribution tells us something intuitive. The population of a state drops off exponentially as its energy increases compared to another state.
Yeah.
Higher energy means fewer occupants, basically, unless you crank up the temperature, of course.
Okay, but there's a potential trap here, right? You mentioned states versus energy levels.
Yes, absolutely critical distinction. The Boltzmann formula gives the population of individual quantum states. Often, though, several states might happen to have the exact same energy. That collection of states at the same energy is an energy level.
And that number of states at the same energy is the degeneracy.
Exactly, the degeneracy. So if you want the population of an energy level, you have to multiply the state population by how many states actually make up that level, by Kc.
Why does that matter so much in practice? Give us an example.
Think about molecular rotation. The ground rotational state, J0, is non-degenerate, so G1. But the next level, J1, for a typical linear molecule, is triply degenerate, G3.
Okay.
So even though the J1 level has higher energy than J0 because it has 3 times as many slots or states available, it's quite possible, especially at moderate temperatures, for the population of the J1 level to be higher than the J0 level. More available parking spots, essentially.
Got it. So degeneracy can really boost the population of higher energy levels.
Yeah.
Okay, we know how things are distributed. Now, how do we quantify the total number of available options? That denominator in the Boltzmann equation looks important.
It is. That sum in the denominator is the molecular partition function, usually written as lowercase q, and it's arguably the central quantity in this whole
The
business.
partition function, Q,
Yeah.
what does it actually tell us? You called it a thermal wave function earlier.
That's a good analogy. It basically contains all the thermodynamic information for a system of independent particles. It's the key that unlocks everything else.
So if it's counting something, what is it counting?
It's giving us a measure of the number of states that are effectively accessible to a molecule, thermally speaking, at a given temperature T.
Accessible states.
Right. Think about it. As T goes to absolute zero, only the ground state is occupied. So Q just becomes the degeneracy of that ground state, GT. Maybe just one, maybe more, if the ground state is degenerate. But as you increase T, molecules get enough energy to start exploring higher energy states. More states become populated, become thermally accessible, and so the value of Q goes up. It reflects the molecule's increasing thermal freedom.
There's that two-level system example in the book, right, where Q goes from 1 at low T to 2 at very high T.
Exactly. At 0T, only the ground state is accessible, Q1.
Yeah.
As T goes to infinity, both states become equally likely, so effectively two states are accessible, Q2. It shows how Q tracks accessibility.
Now, one thing that makes life easier is that a molecule's total energy is often just the sum of different types of energy, right? Like moving around, rotating, vibrating.
Yes, translational, rotational, vibrational, and electronic energy. To a very good approximation, E total plus ER plus EV plus EE.
And that has a really nice mathematical consequence for Q.
It does, because the energy is a sum. The overall partition function, Q, conveniently factorizes, it becomes a product. Q kibo times QR times QV times QE.
So we can calculate the contribution from translation, rotation, etc. separately, and then just multiply them together. That's a huge help.
Massive simplification.
Yeah.
It lets us tackle each mode of motion one by one.
Okay, let's start with translation. QT, molecules moving in a box. The energy levels here are super close together, aren't they?
Unbelievably close.
Yeah.
So close that we can forget the quantum summation and just approximate it with an integral, like in classical mechanics.
And the result of that integral?
It gives us QT V phi. V is just the volume of the container. Lambda is the thermal wavelength.
Thermal wavelength? What's that physically?
Lambda K sort of represents the effective quantum size or blurriness of the molecule due to its thermal motion. It depends on the particle's mass m and the temperature T. Specifically, gets smaller for heavier particles at higher temperatures.
So heavier particles are more classical?
In a sense, yes.
Yes.
Their quantum wavelength is smaller. Because thorium is in the denominator, a smaller O means a larger QT, so a larger volume V, or a heavier mass M, both lead to a much larger QT.
Meaning more accessible translational states.
Way more. If you calculate QT for something like an oxygen molecule in, say, a 100 cubic centimeter flask at room temperature, the number is enormous. It's something like 2 times 10 to the 28.
10 to the 28? That's astronomical.
It tells you that for translation, a molecule has a virtually infinite number of states it can be in. It's swimming in accessible states.
Okay, what about rotation, QR?
For rotation, the energy level spacing is typically larger than translation, but often still small compared to KT at room temperature. So we can often use a high temperature approximation. For a linear molecule like HCl or QO, QR is roughly T divided by C.
Okay, T's temperature, Tr is the characteristic rotational temperature. But what's the sigma?
That's the symmetry number. It's super important for molecules that have some symmetry.
Like oxygen, OO.
Exactly. If you rotate an O molecule by 180 degrees, it looks exactly the same. You can't distinguish the before and after orientations. That indistinguishable rotation means we've overcounted the unique states if we don't correct for it.
So counts the number of orientations that look identical.
Precisely. For OS or co-OS is 2. For a molecule with no rotational symmetry, like HCl, cis is 1. For methane, it's 12. If we forget, our calculated entropy will be wrong because we've counted states that aren't actually distinct.
Got it. Symmetry matters.
Yeah.
Now, vibration, QV, you mentioned we usually don't hit the high temperature limit there.
Yeah, generally not at room temperature. Vibrational energy level gaps are usually quite large compared to KT. Think about infrared spectroscopy. Those absorptions correspond to big energy jumps.
So what does that mean for QV?
It means most molecules are stuck in the ground vibrational state, the CO0. They're vibrationally cold. Higher vibrational states just aren't thermally accessible, so QV is typically very close to 1.
And that means vibration doesn't contribute much to things like heat capacity at normal temperatures?
Right, not until you get to really high temperatures where KT becomes comparable to the vibrational energy spacing. Translation and rotation are usually much more important for heat capacity at room temp.
Okay, so we have Q, this amazing scorekeeper for accessible states, broken down by motion type. How do we actually use it to get a thermodynamic property, like the average energy of a molecule?
There's a really neat mathematical trick for that. The mean molecular energy, which we write as A, is directly calculated from the partition function. You take the natural logarithm of Q, then take its derivative with respect to beta, remember back as 1 kT, holding the volume constant, and then multiply by mech to 1.
A bit of calculus on L and Q, and when we do that for translation and rotation.
We get results that should look familiar from basic physics. For translation, AT comes out to be exactly 32 kT.
3 degrees of freedom, half kT each, equipartition.
Precisely. And for a linear rotor at high temperature, ATR comes out as KT.
2 rotational degrees of freedom, half kT each.
Exactly. The equipartition theorem just pops right out of the quantum statistical mechanics. It's a beautiful consistency check. For vibration, the formula is more complex. But if you could reach very high T, where T is much larger than the vibrational temperature seen, then Ogawa would also approach KT, KT2 for kinetic, KT2 for potential energy. But again, that high T limit for vibration is rarely met.
Okay, so this works beautifully for independent molecules, but molecules aren't always independent, right? They interact, especially in liquids or real gases.
Right. That's a crucial limitation of the molecular partition function Q. To handle interactions, we need to step up our game. We move from thinking about one molecule to thinking about the entire system, and we introduce the concept of the canonical ensemble.
An ensemble, like a collection.
Exactly. Imagine making a huge number, like Avogadro's number, of mental copies of your entire system, same N molecules, same volume V. Then imagine putting all these identical systems together in a giant thermostat so they all share the same temperature T. That imaginary collection is the canonical ensemble.
Okay, so it's a way to think about the statistics of the whole system at once.
Yes, and instead of the molecular partition function Q, we now use the canonical partition function, usually capital Q. Q describes the probability of finding an entire system within the ensemble having a specific total energy, EI.
So Q is for the whole system. Q is for one molecule, if independent. How are Q and Q related?
It depends on whether the particles are distinguishable or indistinguishable. If they're distinguishable, like molecules locked in specific sites in a crystal.
Like assigned seats.
Perfect analogy. Then Q is simply Q raised to the power of n, the number of molecules. Q equals Qn. Each molecule's state contributes independently.
But what about gases? The molecules are identical and whizzing around, swapping places all the time. They're indistinguishable.
Right. General admission tickets. In this case, just using Qn massively overcounts the distinct states of the system because swapping two identical molecules doesn't create a new system state.
Ah, because molecule A here and molecule B there is the same state as molecule B here and molecule A there if they're identical.
Exactly. To correct for this overcounting of permutations, we have to divide by n the number of ways to arrange n items. So for an ideal gas of indistinguishable particles, Q equals Qnn.
That n factor seems really important. Is it just a mathematical fix?
Oh, it's fundamental. Without it, the calculated entropy wouldn't be extensive, meaning if you doubled the size of your gas sample, the entropy wouldn't double, which we know experimentally it must. Dividing by n ensures that entropy scales correctly with the amount of substance. It fixes the so-called Gibbs paradox.
Okay, that makes sense. It connects back to the very nature of identical particles. So now that we have Q for the whole system, we can calculate the system's average energy, E, right?
Yes, using the exact same mathematical relationship as before, but now with Q instead of Q, the average energy of the entire system, E, is related to the derivative of ln Q with respect to beta. This allows us to account for interactions if they're built into the system, energies EI used in Q.
All right, this is powerful. We can now bridge to the big thermodynamic functions. Let's talk internal energy, U, and the big one, entropy, S.
Okay, the internal energy, U, at some temperature T is pretty straightforward. It's just the energy the system would have at absolute zero. Yeah, basically the sum of ground state energies plus the total average thermal energy E that we just figured out how to calculate from Q, or N times A if molecules are independent.
So UO yields plus E, and from U we can get the heat capacity.
Directly. The constant volume heat capacity, CV, is just the derivative of U with respect to temperature, du dt, at constant volume. And since U gets contributions from translation, rotation, vibration. CV is also a sum of contributions from each mode that can actually store thermal energy at that temperature.
Which, again, at high T, we could estimate using equipartition by counting active modes.
Correct. For instance, a monatomic gas has 3 translational modes, so CV is 32 R per mole. A diatomic gas adds 2 rotational modes at high enough T, so CV approaches 52 R.
Okay, now for entropy, S, there's that famous equation.
Ah, yes. The Boltzmann formula for entropy, S equals K log W.
S equals K log W.
Simple looking but profound. Absolutely profound. K is Boltzmann's constant again.
Yeah.
And W here is the weight way. The number of ways is associated with the most probable configuration of the entire system. Remember W from the beginning.
Yeah, the number of ways to arrange the molecules for a given population distribution.
Right. So entropy is directly proportional to the logarithm of the number of microscopic ways the system can realize its most likely macroscopic state. More ways mean more disorder, more spread, higher entropy. It's the statistical definition of disorder.
And it connects to the third law too, right?
Perfectly. As you cool a system down towards absolute zero, T or zero, all the molecules ideally fall into the single lowest energy ground state. There's only one way to arrange them then.
So W becomes 1.
W becomes 1, and the natural log of 1 is 0. So S approaches 0 as T approaches 0. The third law of thermodynamics emerges naturally from the statistics.
That's elegant. Now, for a specific case, the Sackur-Tetrode equation gives the entropy for a simple gas. What does it tell us?
It gives the molar entropy of a monatomic perfect gas. It explicitly shows how translational entropy depends on macroscopic variables. Entropy goes up if you increase the molar volume, Vm.
Makes sense. More room to move, more accessible states.
If you increase the temperature, T.
More energy to access higher states.
And interestingly, if you increase the molar mass, Em.
Why mass?
Because remember, Qt depends on EO and depends on airplanes. So heavier atoms have smaller thermal wavelengths, meaning their translational energy levels are packed even closer together. That denser packing means vastly more states become accessible for a given energy input, hence higher entropy.
Wow. So argon has a higher translational entropy than neon at the same temperature and volume just because it's heavier.
Correct. It's a direct consequence of the quantum energy level spacing.
What about that exception to the third law, residual entropy?
Right. Sometimes, even as T approaches absolute zero, the molecules in a crystal don't settle into a perfectly ordered state. There's some randomness locked in.
Why would that happen?
Usually because the molecules can orient themselves in slightly different ways within the crystal lattice, and these different orientations have almost exactly the same energy. So there's no energetic penalty forcing them into one specific orientation as it cools. Carbon monoxide, CO, is a classic example. In solid CO, the molecules can align as CO or OC randomly.
So there's disorder frozen in at 0K.
Exactly. If each molecule has, say, C's possible orientations it can randomly adopt, even at T0, then the weight W isn't 1, it's S raised to the power N for N molecules. Using SEKLW, the residual molar entropy comes out as RLNS for CO with 2 orientations, SM0, all LN2.
So the third law, S is 0 at T0, only applies to perfect crystalline substances in their true equilibrium state. Fascinating. Okay, we've built up all this machinery. Let's get to the ultimate goal for chemists, calculating Gibbs energy, G, and the equilibrium constant, K. This is where it all comes together.
This is the payoff, absolutely. We can express the Gibbs energy, G, using the canonical partition function, Q. The resulting equation, especially for a perfect gas where Q equals QNN, holds a really deep insight. It shows that G key, G0, the change in Gibbs energy from absolute zero, is essentially proportional to the logarithm of the average number of thermally accessible states per molecule.
Okay, say that again. Gibbs energy relates to accessible states.
Yes. The fundamental thermodynamic drive to minimize Gibbs energy is, from a molecular perspective, the drive to maximize the number of thermally accessible states. Systems naturally tend toward states where they have the most microscopic freedom, most options available. Lower G means more accessible states.
That connects thermodynamics directly to molecular possibilities.
Yeah.
Amazing. And this leads straight to the equilibrium constant, K.
Straight there. We know the standard reaction Gibbs energy, a Grenoble rho, is related to LNK. So we just substitute the expressions for G derived from Q for all the reactants and products into that relationship.
And out tops an equation for K based purely on molecular properties.
Exactly. The master equation for the equilibrium constant K essentially looks like this. K is proportional to a ratio of partition functions. The Q values for all the product molecules multiplied together divided by the Q values for all the reactant molecules multiplied together, and then that ratio is multiplied by an exponential factor.
An exponential factor.
Yes, specifically e to the power of minus re-ERT. Here, Curie is the difference in the ground state energies between products and reactants. Just the energy difference at absolute zero. Purely electronic energy and zero-point vibrational energy.
Okay, so K depends on two main things, the ratio of Q's and this ground state energy difference term.
Precisely. And this equation beautifully reveals the physical tug-of-war that determines equilibrium. That exponential term, EERT, represents the enthalpy effect. It strongly favors the side of the reaction, products or reactants, that has the lower overall ground state energy. Nature likes to go downhill in energy.
Makes sense. Lower energy is more stable. What about the ratio of partition functions?
That ratio, Q products reactants, represents the entropy effect. Remember, Q measures the number of accessible states. So this ratio favors the side of the reaction where the molecules collectively have more thermally accessible states available to them.
Ah, so the side with more complex molecules or molecules with more ways to move and store energy will have larger Q values and be favored by this term.
Generally, yes. Species with higher density of states, more rotational vibrational levels packed together, heavier atoms contributing to translational states will have larger Q values. So equilibrium isn't just about finding the lowest energy state. It's a constant competition, a balance.
A competition between minimizing energy, getting to the bottom of the energy well, and maximizing the number of available states, spreading out the population as much as possible.
You got it. It's the molecular battle between enthalpy and entropy, laid bare by statistical thermodynamics. It tells us exactly why equilibrium lies where it does, based on the properties of the molecules themselves.
That really does tie everything together, from single molecule energy levels all the way to predicting reaction outcomes.
It's a complete journey. We started with Boltzmann figuring out how molecules are distributed. We built the partition function Q to count their options. We used Q and Q to calculate internal energy, U and entropy S. And finally, we arrived at Gibbs energy G and the equilibrium constant K. It truly is the bridge between the micro and macro worlds.
Thinking back over everything, what's one thing that really stands out to you about the power of this approach?
For me, it's the incredible sensitivity it reveals. We saw that the translational partition function, QT, depends on mass through that thermal wavelength.
Right.
So imagine you just swap an isotope in a molecule. Say you replace a regular hydrogen, H, with deuterium H. It's a tiny change, just adding a neutron. But that changes the mass.
Which changes O.
Which changes QT. And that change ripples through the overall Q, then through the canonical partition function Q, which then changes the Gibbs energy G, and ultimately it subtly shifts the equilibrium constant K for any reaction involving that molecule.
So just changing one neutron in one type of atom can actually alter the whole thermodynamic landscape of a macroscopic system, even far from absolute zero.
Exactly. That's the profound power encapsulated in the partition function. It links the tiniest quantum details to the grandest thermodynamic outcomes. That's why statistical thermodynamics is so fundamental, really the backbone of modern physical chemistry.
An amazing connection. Well, thank you for guiding us through that deep dive, and thank you all for listening.